Hey guys, welcome back. This is AP Circuit Notes Part 2. We're going to start with resistors. So the purpose of a resistor is to slow down the flow of current and to drop the voltage. Resistors dissipate energy. So that's a physics word for use up energy, for waste energy. So if you imagine you plug something into the outlet and you get 120 volts, you might not always need the 120 volts for whatever your function is. So I have this hair dryer, I plug it in, it's 120 volts. Maybe I want to run it on the low setting. When the low setting, maybe it only needs 40 volts to heat up the element and blow the air. So what you'd have is one part of the circuit in here, when I flip my switch, would have a resistor, and that resistor would drop the 120 volts down to 40 volts. So it would cut off 80 volts. Maybe the middle one, which is no heat but just blow, only needs 60 volts. So it would take the 120 and cut it down. And the third part of this circuit would be if it's on high, and maybe it just has all 120 volts on that one. I think this is fused too. Inside of the symbol for resistor can be an uppercase R or a lowercase r. The unit is the ohm. This is a capital omega. So omega it looks like cowboys' legs. The way I think of it when I draw it. And it's a squiggly line as a schematic system. So if you think about it, we're slowing down the current. So if we have a squiggly line, the current has to get from there to there. It's going to have to go all the way through. Now we say what strength it is by painting lines on it. The first three lines tell you what the strength is. The third one tells you the guarantee. So plus or minus 5%, plus or minus 10%, plus or minus 20%. The guarantee one is always a metal color. So we get our first two digits from the first two. The third one gives us our multiplier. Resistors do not have a positive and negative side like a battery. You can plug them in either direction, it's not going to make a difference. The ones that we're going to use in here are carbon film. And they're going to vary from 1,000 to 100,000 ohms. And here's so once you look at those painted stripes, you can use this to find out what the value is. If you have a resistor that can be changed, we call that a variable resistor. The symbol is like a resistor, but it has an arrow going at an angle through it. Resistance is going to be dependent on the length of a wire, the cross-sectional area, the material, and its temperature. So resistance is equal to rho L over A. A is going to be the resistivity constant. And in general, as things get hotter, they get more resistant. If you think about these electrons trying to get through, as it gets hotter, it's going to be harder for them to get through. So the resistance goes up. And in the opposite direction, as things cool down, their resistance will be less and less because there'll be less molecules the electrons will have to bounce into. So here's some resistivity constants. I'll show you the example of this real quick. This is on your equation sheet. So a resistance, this is just based on what metal it is and at what temperature. So if this increases, my resistance increases. Let me mute that because I don't want it to, or at least lower it. So you would say that resistivity is directly proportional to resistance. The longer it is, the bigger R goes up as well. So you would say that the length is directly proportional to the resistance. The cross-sectional area is the opposite. As the area gets bigger, the resistance gets smaller. So you would say that the resistance and the cross-sectional area are inversely proportional. Logically, this would make sense. The longer it is, the harder it's going to be for an electron to get through. The bigger it is, the wider, the fatter, the easier it is, right? There's way more paths for it to get from one side to the other. If I make this very thin, it's going to be hard for the electron to get through because it's trying to get through a very small space. And so here's some constants for this. You would never, this is not the type of equation where you'd put numbers in though. Like they would say, if I double the length, or show you a picture and compare the resistors. Resistivity goes down. Certain things are special, and when they get to a low enough temperature, they become superconductors, which means that they have no resistance at all. And this usually happens at very, very low temperatures, although we just recently did it, we, as you say, the scientific community is physicists just did it at room temperature, but they varied the pressure, the atmospheric pressure, by like a ton to do it. So it's kind of cheating a little bit. But we have these superconductors, and we put currents going in these superconductors for decades, and they still just go. So the idea is that 0 Kelvin means that you have no movement of the particles, which is impossible. So your kinetic energy equals 0 joules. And so there would be nothing to get in the way of the electrons. And certain things they can get through where there's no resistance. Our internal energy is equal to the sum of all the kinetic energy of the molecules. It's also equal to 3/2 nRT, where N is the number of moles, R is our ideal gas constant, and T is our temperature in Kelvin. So you can see if this was 0, then you'd have an internal energy of nothing. All right, so Ohm's law is going to deal with this relationship, and you guys are going to do a lab on the computer. The main thing with this is they will, ideal conductors should obey Ohm's law. So what is an ideal conductor? A resistor is. What is not an ideal conductor? Usually not a light bulb. So in the lab, you're going to do values for a resistor, which is meant to just be a resistor, and a light bulb, which is meant to light up. And you're going to see that you're going to have this nice linear relationship for a resistor, but not for a light bulb. And when something doesn't obey Ohm's law, it's considered non-ohmic. Now, this is not a universal relationship. It's not like F net equals ma. It doesn't apply to everything. It's very specific, like kinematics equations, where you have to be with a constant unchanging gravity, or like Hooke's law, where you have to have an ideal spring. There's all sorts of non-ideal springs, and we can't use that. All right, a 3 ohm resistor is attached in series to a 24 volt power supply. Calculate the current through and the voltage across the resistor. How much charge passes through the resistor in 30 seconds. So V is equal to IR. I is going to be equal to V over R. This is 24 volts divided by 3 ohms, not 8 ohms, which is going to give me 8 amperes. And then the definition of current tells me that my charge is equal to I times T. So this is 8 amperes times 30 seconds, which is 240 coulombs. Keep in mind, this equation is not Ohm's law. It is the equation that is derived from Ohm's law. Ohm's law is a relationship between voltage and current for an ideal conductor. All right, so voltage has a symbol of capital V. It also has a units of capital V, which are volts. And this is named, everyone's word is named, Volta. This is named for Alessandro Volta, who was the first one to make a battery, a pile battery. So we put piles of metal on top of each other. The equation for this is V equals IR. What is it? What is this voltage? This is our electric pressure. So it is how much charge can get pushed. It has a bunch of other names. It's known also as potential or the potential difference or that EMF that I mentioned that I don't like. So in our water analogy, it's our water pump. It's the pump. Current has a symbol of capital I or lowercase I. Its units are capital A, and these are amperes, not amps. So there's a difference there. It's amperes, named for Rene Ampere. What is current? Current is the flow of the charge. In physics, we have adapted conventional current. So this is going to be the flow of positive charge. And the formula for this is Q over T, the charge per second. This is known as the definition of current. Resistance is designated by a big R or a little r. It has a unit of capital omega, which is an ohm. This is named for George Ohm. And this is the resistance to the flow of charge. So it is going to slow the current, and it's going to drop the voltage, and it's going to waste energy, which we call dissipating. So it's going to dissipate energy. And again, energy is the thing that's going to connect all of our different sections. So it's important when we think about electricity, we think about it in terms of energy as well. The formula for this is going to be that R is equal to rho L over A, where rho, that's a lowercase rho. An uppercase rho just looks like a P, so it's not very useful to us. Rho is going to be our resistivity constant, which is based on what it's made of and what temperature it's at. L is going to be our length, and A is going to be our area. Like I said, you're not going to put in numbers for this. This is the type of equation where they say if you double this, what happens? If you triple that, what happens? As far as we're concerned, batteries are going to provide a constant potential difference. So very much like Volta thought that he created continuous energy, that's the way we're going to look at it. So if we have a 9-volt battery, it is just going to be 9 volts always. It's going to be the current that changes. How does the current change? It's going to be dependent on the total resistance of our circuit. Resistance is going to be a property of the material. So how hard is it for the current to flow through it? And it is temperature dependent. Current is not a vector, but it has a direction. So why would it have a direction? Because when we discover something new, it's often helpful to try to explain it in terms of something we already know. And so in this case, the thing that they used was water. So it's a water analogy. And so they called the flow of charge current because we call the flow of water current. Well, current has a direction. But current, electric current, is a scalar, not a vector. Current and charge don't get used up. When things don't get used up, we say they are conserved. So very much like in the last section where we weren't getting charge out of nowhere and we had to account for all of it, the same thing happens for current. So the battery provides the potential, the pressure. Everything that it's going through is already full of electrons. They're already exchanging with each other. What the battery is providing is a direction from one way to the other. And as soon as it's hooked up, that current is everywhere. That current is everywhere. It does not get used up. The same amount of current comes out of a battery as goes into it. What does get used up is the actual material that the battery is made of. So over time, that chemical reaction uses up those individual metals, and at some point you don't have enough potential and we stop using the battery. And it's not when it gets down to 0 volts. Like I said, like a 1.5 volt battery starts at about 1.6 and it's useless to us at 1.3 or 1.2. And it still has another potential.